In this demonstration, we're going to show how a magnetic field affects a wire carrying current. So the magnetic force law tells us that the force of a magnetic field on a wire carrying current is equal to the strength of the current times the length of the wire within the magnetic field crossed with the strength of the applied magnetic field to the wire. You may also see this formula written as such. You have this, again, the product of the current times the length times the magnetic field times sine of theta, where theta is the angle between the wire carrying current and the magnetic field. So, for instance, we can show that if we have a magnetic field whose direction is down, and then we have a wire with the direction of the current going from left to right, we can use the right-hand rule to determine the direction of the force on this wire by the magnetic field. And we can do that by just crossing I with B, and we'd find that the direction of the magnetic force is into the page. And applying the second version of this formula, we can see that the angle between the current and the magnetic field is 90 degrees. So sine of 90 degrees is 1. So it would just be the product of the current times the length of the wire times the strength of the magnetic field. So now let's see this played out in a real situation. Okay, so in this demonstration, we have a suspended wire that's connected to a DC power supply. And there's a segment of the wire that's within the magnetic field. And the magnetic field is pointing downward from North Pole to South Pole. Now when I flip the switch, it's going to set up a current running through the wire such that the current will be moving in a counterclockwise direction. So the segment within the magnetic field, I can point my fingers in the direction of the current, and since the magnetic field is pointing downward, I can use the right-hand rule and know that the force due to the magnetic field will be pointing this way into the magnet. So when I flip the switch to the left, that's exactly what happens. And when there's no current running through the wire, again, the wire will eventually go back to equilibrium in its equilibrium position. Now this switch is reversible, so that if I switch the switch closed in the opposite direction, it sets up the current in a clockwise direction. So if it sets up the current in a clockwise direction, we can expect, using the right-hand rule, that the magnetic field will be going, the force through the magnetic field will be going in the opposite direction. So when I flip the switch, you can see that the suspended wire is now being repulsed away from the magnet.